we have the next
Yes,
speaker, Maxim Braverman, the semi-classical Weyl law on complete manifolds.
Okay, so I'm grateful to the organizers and very glad to speak here. So I'll try to keep my talk very, very basic. It's about Weyl law, and as in fact, it's the story which is many interesting stories and analysis. Started with Hermann Weyl in 1911. Hermann Weyl discovered the following remarkable theorem. If you consider a domain in Rn, you consider R2 or R3, but it doesn't matter. So we have something like region in R2, for example, that's omega, and we consider the Laplace operator, and I will always use what people often call geometric Laplace with negative signs. Negative sign of d2 xi squared. So this is a positive definite operator. And we consider, say, Dirichlet boundary conditions here, and then we can ask about eigenvalues of this operator, and the eigenvalues will be, it has discrete spectrum, so we have eigenvalues like number 1, smaller equal than number 2, smaller equal and so on, and they tend to infinity. And you can form what is called spectral counting function. The spectral counting function n of lambda just measures the number of eigenvalues which are smaller or equal than them. So we just cut it somewhere here and count how many eigenvalues you have here. Of course, count it with multiples. And now what Hermann Weyl discovered is that there is an asymptotic. This number n of lambda tends to infinity when lambda tends to infinity. And it tends to infinity in the following ways. Asymptotically, it's equal to lambda over 2 pi n. Some constant omega n. This constant is the volume of the unit ball in red, and it's multiplied by the volume. So this notation basically means that if I divide this by that, then the limit will be equal to this. So that's the basic Weyl law, and there are lots and lots and lots of generalization in this law, and improvements and so on. So let me mention a couple. So a couple of generalization. First, you can consider not just the Laplacian, but the Schrödinger operator. The Laplacian, remember, I always have positive Laplacian plus a potential, and so that's the Schrödinger operator. And we will assume that V of x is infinity. Sorry, I'm jumping. Say about it. So then you have a very similar law. Another generalization is if you take closed manifold instead of M, closed manifold, instead of domain omega, you also have the same type of Weyl law. You will have volume of M instead of volume of omega, and so on. Another generalization, which is very important for my talk, is what is called the semi-classical one. The semi-classical means that you introduce the Planck constant, so your Schrödinger operator will be of the form h squared delta plus v of x. And Planck constant is very, very small, so mathematically we think about it as tending to 0. And now we consider a new counting function, and lambda h. So now, given h, we consider the number of eigenvalues of this operator, which are smaller than that. And now we can fix lambda and ask what happens when h tends to 0. When h tends to 0, you will have more and more eigenvalues smaller than lambda. And the theorem, which is the semi-classical Weyl law, says, well, to start with closed manifold. And then this n lambda h. So now I fixed lambda is fixed, and I'm changing h, and I tend h to 0, and the answer is the following. H to n, and then basically very similar things to what was there. Let me write it and then explain. It will be the volume of the set where c squared plus d of x is less equal than lambda. Now, what's this? So this c and x are elements in cotangent space. So x is a vector. If you're not in geometry, you can think just about direction. So c and x lie in cotangent space. And so inside this cotangent space, we consider the set of points which satisfy this condition. And you consider the volume of it. So this cotangent space is, roughly speaking, R2n. It's 2n dimensional space. And now we have xc and dimensional c and dimensional x. So this thing is a set, bounded set in 2n dimensional manifold, and we consider it so. So that's the semi-classical Weyl law. So basically, we have classical Weyl law and semi-classical Weyl law. There are two versions. The semi-classical is more relevant for what I'm going to say today, but for a while I will talk about this. Now, there are further extensions to non-compact fields. So it also has a long story. For example, you can, instead of omega, you can consider Rn. And then, well, if you talk about classical Weyl law, you have to change it a little bit. So this volume of omega will be changed by something similar to this. I won't write it down. If you consider semi-classical Weyl law, then this formula just works. Even on Rn, Cx will be in R2n, v of x tends to infinity. Now we assume that v of x tends to infinity. As x tends to infinity. And then this is just a bounded set, and you can have this theorem. Well, there are also some special. Well, I should say that there are some restrictions in those theorems. Some restrictions on v of x and how v of x tends to infinity. There are also generalizations to the case when v of x is not smooth. I won't talk about it. But for smooth v of x, we still need some condition on how fast it grows to infinity or how its derivative grows to infinity. There are some unbounded subsets in R. And then we put Dirichlet boundary condition or Neumann boundary condition, and then we have similar results. And that was done in 70s mostly, but then there are sort of more realization to non-compact setting. People consider something like asymptotically Euclidean manifold. That means that outside of a compact set, my manifold looks like Rn, but inside it could be some manifold, it could be some topology, asymptotically hyperbolic manifolds with cylindrical ends. So those are this non-compact manifold, but the non-compact part looks like a cylinder. In all these cases, well, and in all these cases, people needed some distance of V on how fast V grows and how fast the derivative of V grow. And the way it was done, basically people built some kind of pseudo-differential calculus on adapted to these geometries and used. The first result, which is not like this, was very recent. It's in the beginning of this year, 2025. Churchill died, and John Ronk Young, they prove both classical and semi-classical. Cases for manifolds. Now, we have any manifold, what is called of bounded geometry. Well, I won't define it precisely, but roughly it says that curvature is bounded and the radius is bounded with some conditions. On growth of V. So we need some type of replacing homogeneity of V. It should be somehow growing in controlled way, and we have manifold of bounded geometry. Now, as I said, they have both classical and semi-classical case. Recall that classical is when you have just this Schrödinger operator and you are interested in spectral counting function, behavior of spectral counting function when lambda tends to infinity. And semi-classical is this one when you fix lambda and then h to infinity, and you are interested in spectral. So they proved both, and now I'm coming to my result, also 2005. It's very recent, and so I consider any complete Riemannian manifold. So basically, no restriction on the geometry of manifold. Complete means that every curve which escapes to infinity has infinite length. I consider the semi-classical case. And the only assumption I have is that V of x tends to infinity as x tends. So no restrictions on how fast. Let me, before I continue, as you see, I consider the semi-classical case. There is no way to get classical with my methods. And if you're absolutely certain that for classical Weyl law, you will need some conditional control. It's not true for general V. But semi-classical is true for general V. And the theorem is that the semi-classical Weyl law sorry, technical difficulties. So the semi-classical Weyl law holds, and let me just recall you for the semi-classical Weyl law that this condition, we're considering volume of the set, and even if C is equal to 0, remember V tends to infinity at infinity. V of x is certainly here, if this is satisfied, and certainly V of x is smaller than lambda, and that means we're on the compact part of me. So the whole observation, the important observation is, so that's I copied here, this semi-classical Weyl law. Let's look at it. So this all lives in the compact part of the mean. And that's the main idea of my approach. So we have something. So we have our non-compact manifold, but for this, remember we fixed lambda. So our Weyl law depends basically only on this part. So all our computation on the right-hand side depend only on the on a compact part of our manifold K, and in the complement V of X is bigger. Well, it's not correct here. It's bigger than lambda. So now the idea of the proof is the following. The idea of the proof, minutes basically. So what's the idea of the proof? So we use a partition of unity basically. We construct two functions, phi of x, smooth function with values in 0, 1, such that maybe I write it on the side. So the condition are, first of all, phi of is equal to 1 when x is equal. So phi is 1 here, and then it decays to 0. It's support phi. And the third condition is that phi squared plus. So that what it means that phi is actually equal to 0, okay, because here phi is equal to 1. 1, this must be 0. So phi is supported somewhere. And usual partition of unity is when phi plus phi is equal to 1, or what phi squared. And then there is a lemma, classical lemma, which is called IMS, Ibragimov, Morgan, and Simon localization. And I wrote it here because it's long. That's the localization formula. What does it say? It says that my operator H has the term which is supported here, a little bit supported here in any case, in the compact part. There is part which is supported here. And there are this thing here. What is meant by this is just a commutator. The H is B times A. Oh, minus.
So may I ask a question?
Yeah, sure. Well,
you show this tube. Do you mean that this is so this manifold has only one end, or it may have several ends, and for every
no,
of them?
it's just symbolic. It's just non-compact manifold. It doesn't have to have. It's not a cylindrical entity. Any non-compact manifold, complete, and we just take a compact part inside. We just take a compact part inside it. No restrictions.
But on this end, or on this tube, or out of this compact set, the behavior should be so you just assume that the volume is greater than lambda. Yes, this is
not the volume, the potential V. Remember,
potential,
we had this A, which is H squared.
This is potential. The
Delta
potential is greater.
plus V. Yeah, so it's basically how I define K. I consider K, but maybe to be accurate, I need lambda plus 1. It's part where V is bigger than lambda plus 1. So K is where V is smaller than lambda plus 1.
So formally, so if you want to, for instance, confine yourself with with connected sets. So if you have several ends, then you have factorization.
Connectedness doesn't play any role. It could be disconnected. I mean, my manifold can contain several components. So
yes. I mean that you can write not only two functions but several functions. One of them has compact support.
Yeah,
and
but I don't need several.
Yes.
All the rest on different ends to be combined. Not important.
No. The question. May I ask you? The question is: you have a bilinear part which depends on phi. So it's this, for instance, the sum of these brackets, yes, is not linear in phi. Is linear.
No, it's not.
So if you if they have the disjoint support, it does not matter. Yes.
It doesn't matter. It doesn't.
Okay. So I understand.
So you'll see in a second what it's very simple from now on, because basically the idea is that this thing is bigger than lambda. Now, those things are small. So they are the size of h squared. So they estimated by h squared times samples. And so they're bounded and they're estimated by h squared. They're supported in the place somewhere in between here where differential of p phi and psi, differential of phi and psi are not zeros in this place, and only here it's supported, and there are actually zero order operators, and they're of size h squared. So they tend to zero, basically I ignore. But it's some technicalities, but more than some technicalities I ignore. And now this thing is basically on a compact set of K. And now I can do the following thing. I can just construct a compact manifold, which I basically take K and complete it with this. And I can consider extent V of x here somehow. And I consider the Schrödinger operator on here. And I know that the right-hand side of my semi-classical Weyl law will be absolutely the same for this manifold. And the only thing now to prove the Weyl law, I need, because I know it on this compact manifold. So now I need it on non-compact. I need to compare the spectral counting. And standard properties of spectral counting functions say that, well, small part, much, and if you add, if you add a big part, it doesn't affect. And this one is the same here and here. So by this comparison, well, I'm skipping some technicalities, but this technicalities is half a page calculated. So actually the paper I'm talking about has 3 pages. So modeling these technicalities, you immediately get that n, well, let me stay on my original manifold n, is approximately the same as n on 18 in this compact manifold. And now what? Because we know the Weyl law for this, and the right-hand side is exactly the same. Now let me finish by saying that why it doesn't work for non-compact for classical Weyl. For classical Weyl law, you cannot have this fixed k. So you have to change lambda. For classical Weyl law, you're changing lambda, you bend lambda to infinity. And that means that for different lambda, you're taking bigger and bigger part. And so that means you can try to use computation, but the computation manifolds will change. And so you cannot do it as easy. So this method works for semi-classical, doesn't work. But for semi-classical, it kind of tells us that in differential geometry, if you have complete, you have the semi-classical. So I'm basically finished. As a last speaker, I'm privileged to thank the organizers who organized this great conference under hard conditions. So let's suggest to clap or by hands or using technology. You can clap using this, I think.
Thank you very much for interesting talk.